So let me briefly introduce the aims of this work, where we have provided new set of analytical solution for the average strain energy density in notches, orthotopic, reduced notch in orthotopic bodies, mainly under mode 1 loading conditions, as well as to derive some expression, usually to assess the control radius for this class of materials. Thirdly, we carried out a quite comprehensive numerical validation of the analytical solution determines for the strain energy density. And eventually, we have applied the approach to assess the static strength of notched components made of short carbon and glass fiber reinforced polymers, considering different materials, as we will see later, and different geometries. So let's move back to the fundamentals of the so-called asset criterion, which can be dated back to a work dated 2001 by Lazzarini and Zambardi, who postulated that the static and the fatigue strength of notched components is controlled by the strain energy density average over circular sector surrounding the notch tip. These are the relevant expressions that they have been derived for the average strain energy density. As you can see, it depends on the mode 1 and mode 2 notch stress intensity factor, as well as on the size, the radius of the control volume. And in this work, they initially apply the criterion to summarize a large bulk of data related to the static strength of brittle or quasi-brittle materials. And on the left-hand side, you have an example of application in this field, as well as the fatigue strength of steel welded joints, and later it was extending also to aluminum welded joints. Some years later, still not working, sorry. Some years later, Lazzarini and Berto extending the criterion to reduced notches. The schematics are represented here. They consider a crescent moon-like control volume located at the head of the notch tip. These recall the contour lines of the strain energy density close to the notch tip, and they analytically evaluated the strain energy density or average over this kind of volume. The final expression is that reported here. As you can see, it is very simple. This parameter f can be seen as a sort of averaging factor and contains a lot of analytical manipulation related to the integration of the whole stress field within the control volume. And in the same works and also in subsequent works, they apply successfully this approach to assess the static strength of a large bulk of different materials and different geometries depicted in this slide. So now let's move the attention to orthotropic solids, and let's try initially to understand why there is the need to reformulate this criterion for this class of material. And to understand properly this, we can take a look to the stress distribution in front of notched plates made of orthotropic material, because different from the isotropic case, for this class of material, the stress distribution is significantly affected by the elastic properties. And this is evident from this figure, where for a given geometry, the stress field is plotted for different materials. In particular, the black lines and black signals are related to a material which is very stiff in the loading direction, so in the direction normal to the bisector line. In that case, you have a very high stress concentration at the notch tip, but the stresses, in particular, this is the normal stress, is rapidly decreasing, moving apart from the notch tip. This is not the case of the red condition, which is representative of material which is instead very steep, very stiff along the bisector line of the notch. In this case, you can see you have a lower stress concentration at the notch tip, but the stress gradient is, let's say, milder. And we have, some years ago, derived this set of equations in order to explain the important role played by the elastic property in the stress distribution of notching component in orthotropic materials. In this picture, you can see also that the notch opening angle for a given material has a non-negligible effect. Indeed, increasing the notch opening angle, the stress distribution, let's say, is less steeper. It's less steep. So Let's now move to the equivalent strain energy density. As we have seen, the stress field is significantly affected by the elastic properties of the material, and so it is expected, within reason, that the same happens to the strain energy density average over the control volume. This is the reason why we cannot no longer use the expression that was previously derived by Lazzarini and Zambardi and Lazzarini and Berto, and we need to completely reformulate the problem from the very beginning. And this is what we did recently, considering both sharp notches and reduced notches. And I would like to focus the attention on this final equation for reduced notches, which is very easy in principle, and is documenting the fact that the average strain energy density within this control volume, we have maintained this, for simplicity, the same shape proposed by Lazzarini and Berto, can be assessed invoking the strain energy density evaluated at the notch tip, multiplied by this factor, which is nothing but an averaging factor, and which depends by all this integration factor across and within the contour volume. These equations are transcendental equations, cannot be derived in closed form, and they need numerical integration. And they account both for the local geometry, so the notch root radius as well as the notch opening angle, and for the elastic properties of the material we are dealing with. Here's some plots of the solution in order to focus the attention and understand properly which are the main parameters affecting this quantity when evaluated within the control volume. As you can see, the strain energy density, the averaging factor, so the normalized strain energy density, depends on this ratio RC over R0. RC is the radius of the control volume, which is thought as a material-dependent parameter. Differently, R0 is a geometrical parameter which depends on the notch opening angle. And you can see here, there is also a significant effect, as expected, of the elastic properties of the material. This parameter psi summarizes the effect of the orthotropicity ratio. It depends on the ratio between, mainly on the ratio between the elastic moduli in the two principal elasticity directions. And C equal to 0.25 is representative on an isotropic material. C values lower than 0.25 are representative of material which is very stiff in the loading direction. So, for example, a unidirectional short or long fiber composite material. Conversely, C values larger than 0.25 are representative of material which is very stiff along the direction of the bisector line. On the right-hand side graph, you can see that also the notch opening angle has a significant effect on the values and the distribution of the average strain energy density. So these are the main parameters affecting the problem and the phenomenon. This ratio, the elastic properties summarized, which can be summarized by using this factor and the notch opening angle. So by taking a look at the result that I just showed you, we can also clearly identify two main regions in the distribution of the average strain energy density as a function of RC over R0. We have on the left-hand side the first region where the average strain energy density is not significantly different in comparison with the value evaluated at the notch tip. This is because the control radius over the R0 is very small. And so you are including your calculation only the regions which are very close to the tip. Conversely, increasing the value of this ratio, you can move to this region where the control radius is very large. And so in this region, there is no significant difference between the reduced notches in the calculation and the corresponding pointed V notch. So the notch root radius with the notch with the same notch depth, but a notch root radius equal to 0. According to this region, we can use this simplified equation to assess the average strain energy density. Starting from this equation, which depends on this parameter, which is the generalized stress intensity factor, calculated for the reduced notch, we can substitute this expression for this parameter, which can be calculated as a function of the maximum tip stress. And we can calculate analytically this point where this is the intersection of these two asymptotes. This can be calculated in closed form, this particular value, and it depends on the elastic properties of the material as well as the notch opening angle. Using these results, we can also determine the actual distribution variation of the strain energy, the average value of the strain energy density using the mathematical method of asymptotic matching. And the resulting equation is this one, which is very simple, much simpler than in comparison to that I showed you before with the explicit integration of all the stress field within the domain. And so it's particularly useful by the practical point of view when we want to apply this criterion to real data. The first step of validation of the approach was numerical validation. This was necessary because we have used for calculations some expression for the stress field which are not exact. They are accurate but approximated. The approximation is very good, and indeed you can see the comparison between the theoretical prediction and the numerical data, which are the symbol, is very satisfactory. This is an example for a notch opening angle equal to 135, and there is, let's say, a more comprehensive validation that we have carried out. We have considered different materials, from materials very stiff along the loading direction to materials which are very stiff along the bisector line of the notch. So we can conclude that the calculation, the accuracy of the calculation is very satisfactory. Another important point to apply this criterion, to reformulate the criterion for orthotopic material, was the method related to the calculation of the critical radius, which was addressed as well. This is the exact expression that can be obtained using the strain energy density expression for the point EV notch case. You can see it depends, as for the isotropic case, on the critical value of the notch stress intensity factor for the point EV notch, as well as on the static strength of the base material. And within this factor, in particular within the integral IC, there is the explicit effect of the material properties, the elastic properties of the material in particular. We have also derived some approximative analytical expression in order to assess the critical radius, starting not from the point EV notch case, but starting from experimental data related, for example, to reduced notches with different notch root radii. And the radii, this could be particularly useful for practical application. So moving to the next step of validation, we have applied the criterion, the reformulated criterion, in order to assess the static strength of notched components made of short fiber reinforced polymers. We have considered both glass fibers and carbon fibers and different metrics, PA and PPS. The PPS is, let's say, more brittle as matrix. PA is as a more ductile behavior. In the case of PPS, we have obtained notched geometry, both starting from injected plane plates and molding and machining the plates, as well as obtaining directly the notched geometry by injection molding. So in order to include also the effect of the process in the definition or in the orientation of the fiber within the specimen. We have considered different materials and different geometries, as you can see, from semicircular notches, lateral V notches, U notches, in order to have a quite broad validation of the criterion. So we have, for all the cases, we have calculated the critical radius and applied the expression that I showed you before. And there is an example of application for one case. As you can see, the red symbols and lines are related to the experimental data report in terms of nominal stress. Conversely, I'm going to the end. Conversely, as you can see in the case of nominal stress, the scattering of the experimental data is quite broad due to the significant effect of the notch root radius. But when we convert it in terms of local strain energy density, the scattering is very reduced and all the data flow within the same very narrow scatter band, documenting the accuracy and the validity of this criterion also for this class of material. This is an overview of all the experimental data that we have obtained, and in those cases you can see that a summary in terms of strain energy density is extremely effective. So coming to the conclusion, I would like simply to summarize what we did. We have determined analytically expression for the average strain energy density. So we have reformulated the approach for autotropic materials, documenting that the main parameters influencing this quantity are the RC over R0 ratio, the notch opening angle, and the elastic properties of the material. We have provided approximated but accurate analytical expression in order to assess both the asset and the control radius size. We have validated this expression numerically, comparing with numerical data, and we have applied the criterion in order to summarize the static strength of notched short fiber reinforced composites. And as a main conclusion, I would like to state that this criterion, which was formulated more than 20 years ago for isotropic material, has appeared to be very effective also for this class of materials, composite materials, which are very complex because they are characterized by a very complex morphology. And that's all from my side. Thank you for your attention.